Okay, so we're going to finish up talking about vectors. We talked a little bit yesterday about equilibrium when we were going over homework. Equilibrium, again, is when the net force acting on the object is 0 newtons. We talked about the equilibrant force. That's what it's called, that single force that causes equilibrium. So if you have 2 or more forces acting on an object at the same time, and you're able to find the resultant of those forces, the one force that you could add to it that would cause the resultant force or net force to be 0 is called the equilibrant force. And again, you find that by finding the resultant of the forces acting on the object, and the equilibrant force would be equal in size and opposite in direction to that resultant. Opposite in direction, again, you would either add 180 degrees to it if it's between 0 degrees and 180 degrees, or you would subtract 180 degrees from it if it's between 180 degrees and 360 degrees.
You have a call, line 1, Mr.
So a real quick example of that is if we have start with our coordinate plane, and let's say we have a 4 Newton force acting to the east and a 3 Newton force acting to the north. The resultant would be 5 newtons. And we would need to find this angle. It's not a very good color for this screen. Let me change that real quick. That angle would equal the inverse tangent of the opposite side, which would be the 3 newtons, over the adjacent side, which would be the 4 newtons. Inverse tangent of 3 over 4 is 36.87 degrees. I'm just going to round that off to 36.9. So this is 5 newtons at 36.9 degrees. To get the equilibrant force, it would be equal in magnitude, so 5 newtons, but opposite in direction. So we would add 180 degrees to that 36.9, which would be 216.9 degrees. So that's once again how you find an equilibrant force. You find the resultant of the forces that are acting on the object and the direction that that resultant is acting in, and you add 180 degrees to it. Once again, if your resultant is down here somewhere, you would just subtract 180 degrees to get it going back in the other direction. All right. One of the last things we have to talk about with vectors is forces on an inclined plane. An object's weight always acts straight down toward the Earth. So when an object is on an inclined plane, that weight still acts straight down toward the Earth, and it can be broken up into 2 different components. One component is parallel to the inclined plane. We call that force parallel. And the other is perpendicular to the inclined plane, which we call force perpendicular. Pretty tricky. So because the perpendicular force perpendicular is perpendicular to the plane, and the weight of the object is perpendicular to the ground, then the weight of the object and the perpendicular component of its weight make a similar triangle to the triangle that's formed by the inclined plane and the ground itself. So the angle formed by the weight and the perpendicular component of the weight is the same as the angle of the inclined plane. And because of that, we can find the parallel component of the weight by taking the weight itself times the sine of the angle of the inclined plane, and the perpendicular component would be equal to the weight times the cosine of the inclined plane. Remember, we changed this to FG instead of W. So you might want to take your green card and change those W's to FG. So to put what I was just talking about into a picture, if this is our inclined plane and it's inclined at, this looks like maybe around 20 degrees. If we have an object sitting on that inclined plane, its weight still acts straight down toward the ground. The perpendicular component of its weight would be perpendicular to the inclined plane. The parallel component of its weight would act parallel to the inclined plane. So this is F perpendicular, this is F parallel. So once again, because FG is perpendicular to the ground and F perpendicular is perpendicular to the plane, this angle in here, using our skills of geometry, is also 20 degrees. Have a similar triangle formed. And then we can take F parallel and move it down here so that it closes up that triangle. And we can see that F perpendicular is the adjacent side to the angle formed, and F parallel is the opposite side to the angle formed. So that's why F parallel is equal to the weight, Fg, times the sine of the angle, and F perpendicular is equal to the weight times the cosine of the angle. So if this object has a weight of 300 newtons, we would find F parallel by taking 300 times the sine of 20, and F perpendicular would be 300 times cosine of 20. Now, because F parallel is really the one that acts down the plane, if this object were to slide down the inclined plane, that would be the applied force. And because F perpendicular is perpendicular to the surface that the object is sitting on, F perpendicular is the normal force when an object is sitting on an inclined plane. Remember before I kept saying when an object is on a horizontal surface, normal force is the same as the weight. This object is not on a horizontal surface anymore. It's on an inclined plane. Normal, once again, by definition, is perpendicular to the surface. So the normal force is now opposite of the F perpendicular. So here's the pretty picture that I drew using the tools on the PowerPoint program. Shows you the same stuff. All right, so if an object is going down the inclined plane, then again the parallel component of the force acts as the applied force. that would cause the object to accelerate down the plane. And then there's still a force of friction acting up the plane because it opposes the motion of the object. So our net force would equal the parallel component of the weight, which is our applied force, plus the negative friction force. And again, the perpendicular component of the weight acts as the normal force. So if we know the coefficient of friction, we can calculate the normal force, or we can calculate the friction force by taking the coefficient of friction times the perpendicular component of the object's weight. So for example, we have a 562 Newton trunk. On an inclined plane that has a 30-degree angle. So here's our 562 Newton trunk. And our inclined plane makes a 30-degree angle. So again, the weight of that trunk goes straight down toward the ground. It has a perpendicular component, perpendicular to the surface of the plane, and the parallel component acts down the plane. That's what makes it want to accelerate. This problem is kind of easy because it tells us that this is a magical frictionless plane. So it wants to know what the acceleration of the trunk would be if this was a frictionless plane. You know what, I'm just going to go ahead and change that a little bit and say that this plane has a coefficient of friction of 0.18. So if we want to know what the acceleration is, again, we would start with the equation for what we're looking for. Acceleration would be net force divided by mass. We have neither one of those things. But we know that if the weight is 562 newtons and gravity is 10 meters per second squared, that our mass would be 56.2 kilograms. Net force takes a little more work. The net force would be equal to the force applied, which, since this thing is going down a plane, the applied force is equal to the parallel component of the weight, plus the friction force. And we want to make sure that that's negative when we put it in here. Okay, again, we don't have either of those things. Parallel component we can get by taking the weight times the sine of the angle. So we have 562 newtons for the weight times the sine of 30 degrees. About 62 times the sine of 30 is 281 newtons. So that's going to be our applied force, parallel component. Now, for the friction force is equal to the coefficient times the normal force. Coefficient is 0.18. Normal force we don't have yet. But we know that the normal force is the same as the perpendicular component to the weight. So that's equal to the weight times the cosine of the angle. So 562 newtons times cosine of 30 486.7 newtons. So that goes up into here. Times 0.18 gives us a friction force of 87.6. And when we put that up into here, we got to make it negative 87.6. That gives us a net force of 281 plus negative 87.6, 193.4. And then when we put that up into here, divide that by the mass of 56.2 kilograms. It's going to have an acceleration of 3.44 meters per second squared. Okay, so if the object is being pulled up an inclined plane, then the force applied is pulling it up the plane. The parallel component of the weight still acts down the plane. So does the friction force. So now the net force would equal the force applied, pulling it up the plane, plus the combination of the friction force and the parallel component of the weight, which would both be negative in that case. Perpendicular component still is equal to the normal force. And lastly, to find the coefficient of friction of the inclined plane, static friction gets overcome when the parallel component of the force or the weight is equal to the friction force. So if you put an object onto something that's going to be an inclined plane and start raising that inclined plane, when you get to the point where the object starts to slide, that's where the static friction overcomes the friction force. At that point, the weight of the object times the sine of the angle is equal to the coefficient of friction times the normal force. And since the normal force is equal to the weight of the object times the cosine of the angle, we can rearrange or add that into the equation, substitute that in the equation for normal force and get that. Then if you take both sides divided by the weight times the cosine of the angle, you'd have weight times the sine of the angle divided by weight times the cosine of the angle. Weight would cancel out because it's on top and bottom, and sine divided by cosine is equal to the tangent. So once the object starts to slide on an inclined plane, the coefficient of friction is equal to the tangent of that angle, whatever angle that is. All right, so that is it. Equilibrium, equilibrant forces, and forces on an inclined plane. Good luck with your homework.